Welcome back everyone to my first math video on this channel. So today we will be discussing areas between area between curves. All right. So we're going to be talking about applications of integration. So yeah, let's start off with areas between curves. So let's just say we have this x and y axis here. All right. So see, we have this x and y axis. Now we have a function. I'll just say it in blue. This is f of x. Now we have another function. I'll just say it in red. Below it, let's just say g of x. Okay? Now we know that with integration, we can just find the area under one curve. So if we want to find the area under curve of f of x from a to b, let's just say, from a to b, what we will do is we will integrate it, right? So we just do, the integral from a to b of f of x. Makes sense intuitively, right? But then how do we find the area between f of x and g of x, you might be wondering. Well, since we want to find this area right here, we can just find the area of f of x and g of x and subtract them from each other. All right? So, to find the area between these two curves, it's just going to be f of x minus g of x dx. Now this is assuming that we are making vertical rectangles, because remember, integration is just a Riemann sum. We're making a tiny sliver of rectangles, kind of like this. Just say this is dx. But yeah, we're making a tiny sliver of these rectangles, and we're summing them all up. But what if we have a different this is area, right? So what if we have a different kind of situation? What if we have what if we have something like this? I'll make it the same height as that. We have our x-axis and then our y-axis. Also, make sure to label your guys' axes. I don't do that because I'm lazy, but you guys should definitely do that. Now, what if we have something that is like this? That is absolutely horrible. I'm so sorry, guys. What if we have kind of a function like that looks like that? Or sorry, I'll do different colors again. And then a function that looks like okay. Now in our previous example, we looked at if it's on the x-axis. All right. And this is now for this to actually work, this formula, f of x actually has to be the top function and g of x has to be the bottom function. For this kind of situation where we want to find from A to B, we are along the y-axis. So we are going to make horizontal rectangles instead of vertical rectangles. So let's just color everything in here, because this is the area, and then switch back to this. Boom. Yeah, so we're just looking at this area, correct? So for this, what we're going to do is we're going to take the red function minus the blue function. All right, so I forgot to label these. This is f, oh my god. This is going to be f of x, and the blue one here is going to be g of x. I hope that makes sense, right? So what is the area going to be, right? It's just going to be from the integral from a to b of or sorry, this can't be actually f of x, guys. I'm so sorry about that. This is actually going to be, because we're along the y-axis, right? So this is going to be g of f of y and g of y. Okay? And yeah. So it's our formula is going to be f f of, guys, I'm not having a good day. F of y. There's supposed to be a y here. Minus g of y dy. And that is how you do. That is area between two curves. All right. Now let's look at some practice problems. So now let's look at some practice problems involving these. So let's take a look at number 1. We want to find the area, or sorry, here's problem number 1. Determine the area, of the region bounded by the graphs of y equals natural log of x, y equals 2, and x equals 10. All right, so let's first graph these so we know what we're looking at. Let's draw our y-axis. Let's draw our x-axis. Okay. Let's just make that a little bit longer. This is going to be our x. This is going to be our y. So the graph of y equals ln x looks something kind of like this. Or I'll use a different color. How about pink? Looks something kind of like this. So this is y equals ln of x. All right. We have the line y equals 2. Now, this isn't going to be to scale. Like, we're just trying to see how these graphs look like so that we can find the area. Okay, so we have the line y equals 2, which is going to be like this. Y equals 2. And we have the line x equals 10, which is going to look something kind of like this. So from this, we can see that the only region that is bounded between these graphs is simply this shaded region right here. All right. So now how do we find the area of this? Well, first of all, we need to find where it intersects here and here, because we know that we're going to make vertical slices, or not slices, but like rectangles, right? So let's just find where the graphs intersect. So we're going to be looking at first we need to set ln x, y equals ln x to 2, because we're trying to find this point right here. So we're going to set ln x equals 2. So that means that x will be e squared, right? So this point is going to be x equals e squared. Now, for this other point, it's touching the line x equals 10 and y equals 2. So this point right here is just going to be 10, comma 2. Now, and actually, I shouldn't even write x equals e to the... Technically, this is e squared times some number we don't know. No, I'm not going to calculate it, but it's not important to know. So now we can just do the integration, right? It's pretty easy at this point. So the area is going to be the integral, definite integral, from e squared to 10 of the region, right? Which is going to be the top function minus the bottom function, which is going to be natural log of x minus 2 dx. Look at that. We've set up an integral that shows this area. That shows this area right here. So how about we just solve this now, right? Yeah, we just integrate. So the integral of ln x, you have to actually use integration by parts. I'm not going to show you how to actually integrate that, but just know that it will become x ln x minus x, right? And the integral of minus 2 will become minus 2x. And we're integrating this from e squared to 10. So plug everything in. You get 10 ln 10 minus 10 minus 20 minus what is that? 2 e squared plus e squared plus 2e. All right. Wait, guys, I just did this whole thing wrong. Never mind. So yeah, we plugged in 10, and now we plug in e squared, right? So it's gonna be e squared ln of e squared minus e squared minus 2e squared. All right. Now simplifying everything out, we get 10 ln 10 minus 30, and then this whole thing will just become minus 2e squared plus e squared plus 2e squared. We'll see that this cancels out with this, and so we're just left with 10 ln 10 minus 30 plus e squared. And that is the area under the curve of this region. Now, I'm going to go over here and say that this is method 1. Because we can also do it using horizontal rectangles. So how about I show you guys using that way? So for this, we are going to need to integrate from here all the way to here. So, oh, that's terrible. We're integrating right there, okay? So how about we, how do we actually do this? This is a good question. All right. I'll let you think about that one for a second. So to do this, what we're going to do is we're going to first find the bounds. So this is going to be method 2. And remember, this was the answer that we got for the first method. So hopefully by doing it this way, we should get the exact same answer. So how about we first need to find the bounds of this integral, right? So because we're integrating from here to here, because we're integrating from here to here, we're going to be looking at the y-axis. So the y values of this is going to be from 2 to wherever or sorry, not 2 or sorry, yeah, 10. It's going to go from y equals 2 to wherever y equals ln x will intersect with that x equals 10 line. So how about we go over here and we say that that intersection point is going to be y equals ln of 10. And I hope that makes sense, because this place right here is just going to be where y equals ln x and x equals 10 intersect. So if you have a system of equations, you're just going to plug that right in. So that means the bound of this new integral is going to become from 2, because that's the bottom part, right? Y equals 2 to y equals ln of 10. ln of 10. And remember from before, if you're doing horizontal slices, horizontal rectangles, it's right function minus left function. The right function in this case is the line x equals 10. So we're just going to say that 10 minus this function y equals ln x. But if we put an ln x here, it's not going to work, because we're integrating. We're going to be integrating with respect to y, right? So we can't put in ln x. So what we have to do is we have to solve for y or x, right? So y equals ln x. So then x will be, but remember ln x, okay, this, I'm kind of confusing you guys a little bit. So ln of, so remember, that's just log base of e x. So that means that if we want to solve for y, that means that x is simply just e to the y. Intuitively, that makes sense, right? So 10 minus e to the y dy. All right, let's just integrate this now. It's pretty straightforward. We're gonna get 10y minus e to the y. Integral of that is just e to the y. And then plug in ln 10 2, get 10 ln of 10 minus e to the ln of 10, which is because e to the ln of 10 is just going to be 10 minus 20, is that 20 to minus e squared? And if you notice, that is the exact same thing. Oh, sorry. So, I kind of made a mistake, though. Because when you actually do this, you actually split it into 2 integrals. And I've kind of forgot to do that, guys. Like, I'm gonna be honest, I'm kind of being lazy and skipping a lot of steps, which is something you shouldn't do. So let's separate this into two integrals, which will be 10 dy minus e to the y dy. So now plug in, so we get 10y from ln 10 to 2 minus e to the, e to the y from 2 to ln 10. So now we just plug in, and 10 times ln of 10 r minus 20 minus e to the ln of 10 minus, is that e squared? But this thing right here can just be written as 10, because e to the ln 10, that's just 10. Yeah, so now we just distribute minus 20. It's going to be minus 10, but that can just be written as minus 30 plus e squared. And if you look back up here, would you look at that? We got the same exact answer as we did down, as we did using horizontal and vertical rectangles. Now let's try another example. This is going to be problem number 2, and we are going to be looking at the area between the curves of y equals x and x equals y squared. So let's graph that out. We are going to get something like that. X-axis and y-axis here. Straighten that. This is going to be x-axis. This is going to be y-axis. So x equals y squared. That just looks like this. It's kind of like a parabola, but like rotated to the side. And y equals x is just this line right here. So we're looking at the area between, so right there. All right. So let's just for this, I think it's going to be easier to use vertical rectangles, so dx. So we actually going to need to make both things in terms of x. So yeah. So let's get that x equals y squared. Let's take the square root of both sides. Square root of x equals y. So now we have y equals x and y equals square root of x. So then we're integrating from where both of these intersect, right? So you know, y equals square root of x and y equals x. So how about we simply, or sorry, we're just trying to find where these lines intersect. So we have y equals x, and then x equals y squared. So you can just plug in for y, so we can get y equals y squared. So y minus y squared equals 0. Factor out of y, you get y minus. So 1 minus y equals 0. So y can equal either 0 or 1. That is where these two curves intersect. So here at 0, comma 0, and right here at 1 comma 1. So we're going to be integrating with respect to the x-axis from 0 to 1. This is the area, right? 0 to 1 of the top minus the bottom. Well, we see that the top is just that parabola looking thing right there, which is just going to be, let me just move everything here to the bottom. Oh my god, bro. Oh my god. You know what? Screw it. Just the area will just be the integral from 0 to 1 of the top curve, which is going to be square root of x minus x dx. So yeah, just integrate this. If we integrate this, we're gonna get. Now, actually, upon setting up this integral, I realized, what if it's easier to do with horizontal rectangles? I'm so sorry, guys. It just came to me, when you're making these videos, you don't really have time to think about this. But yeah, what if we use horizontal rectangles? So that means we're going from 0 to 1. It's the same thing, right? Of top curve, which is going to be y squared minus y dy. And I think this is going to be easier to integrate, actually, because the other one, we were dealing with like square roots and stuff. I'm really not about to deal with all of that. But actually, wait, I made a mistake here, because this should be like this, because the y, remember, it's if you're doing with respect to y, it's right function minus left function. The right function here is actually this one right here, the y equals x, and then the left function here is that curve. So it's gonna be like this. So now we can just integrate. We're gonna get y squared over 2 minus y cubed over 3. It's from 0 to 1. Plugging everything in, we get 1/2 minus 1/3, which is simply just 1/6. That is the area right here. Now for our third and final example, I'll try to I'll ramp up the difficulty just a little bit, but it won't be too bad. So I'm actually gonna I didn't come up with this problem. My professor did for one of the quizzes. So I'm just gonna put it in right now. So we'll just go here. Paste. And boom. All right. This is the problem number 3 that we will do. And y equals 7x minus 6. Let's graph these out. Let's just, graph our things. Label our axes, x and y. And so y equals x cubed is going to look something like this. Something like that. I mean, that's not actually like how it is, but we're just like estimating, right? And the line y equals 7x minus 6 is going to be somewhere down here, right? So I should probably extend this, probably. It's going to be somewhere down here. So Yeah. I'm gonna redraw this whole thing. To better accommodate this graph, okay? So yeah, this is what our graph looks like. So this is y equals x cubed, and this is y equals 7x minus 6. All right, so first of all, we need to find the bounds of our integral. So we need to find where these lines actually intersect. So we can just set them equal to each other. So x cubed equals 7x minus 6. Subtract 7x minus 6 from both sides. It's 7x cubed minus 7x plus 6 equals 0. Now we can't actually factor this, so we are going to have to use the rational roots theorem, which states that it's p over q, where p is the amount of terms that divide evenly into the constant, and q is the amount of terms that divides evenly into the leading coefficient. So that gives us the factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. I'm thinking we use synthetic division. Let's just try something like a 1. So yeah. 1, 0, because there's no x squared, minus 7 and 6. Bring this down 1, 1, 1, minus 6, minus 6, and 0. So our new equation will be x minus 1, x squared plus x minus 6, 0. Now we just factor this. So x minus 1, x plus 3, x minus 2, 0. That means that x will be 1 minus 3, or 2. Now we can just set up the integrals. But remember, we are finding the area... Oh, sorry. We're finding the area between here and here. So these are going to be two very separate integrals, because we have to find each area and then add them together. So how about we do this? How about we do this area right here and then do this one afterwards? So yeah. So will that give us the integral from minus 3 to 1, right? Of that. Let's integrate with respect to x. So our thing on the top will be x cubed, right? Minus that line, so minus 7x minus 6. But that'll, if you're subtracting, it'll become minus 7x plus 6. Dx. And how will we add that to the integral from 1 to 2 of... From 1 to 2, we can see that the line is actually on top of the cubic. So it's going to give us 7x minus 6 minus x cubed dx. Now we just integrate. Pretty easy peasy here. We get 1/4 x to the 4th minus 7 over 2x squared plus 6x, evaluated from minus 3 to 1, plus 7 over 2x squared minus 6x minus 1 over 4x to the 4th, evaluated from 1 to 2. It's supposed to be a 1, by the way. Right? So yeah, just plug everything in. Now I'm not gonna do all the arithmetic, but you should get, if you plug everything in, you should get 131 over 4. You know, you do that in your calculator, but I'm not here to sit and add a bunch of fractions, so yeah. Just plug these in, you should get 131 over 4. And that is it. That is, I think, what you need to know for areas between curves. That covers kind of the basis of what you need to know, right? If you guys enjoyed this math video, my first math video, then thank you. I'll keep making more like this. hopefully as I get used to it, then I'll make less mistakes and stuff. So yeah, I hope you enjoyed that video. Next video, I will be covering volumes of Solids of Revolution. Thank you all so much. I'll see you all next time.